Alright, so in this video we're going to be looking at the reaction mechanism for hydrohalogenation of alkenes. That is hydrohalogenation of alkenes. So we can get a lot from the name just alone, right? So we're talking about alkenes. This is a reaction involving alkenes. So that is a carbon-carbon double bond is going to be involved. And what we'll also see is hydrohalogenation. Hydro is referring to the hydrogen, and halogenation is referring to our halogens, which we represent with the letter X. So an X we use to represent our halogens. So our halogens, these include elements like our fluorine, chlorine, bromine, and iodine. So these are all examples of halogens. So we can have things like HBr, HCl, HF, HI. When these compounds react with an alkene, we see our hydrohalogenation of alkenes reaction occurring. So let's look at a simple example and work out the mechanism. So let's say we have this simple, rather symmetrical alkene compound here. So here we can see our double bond, so we're dealing with an alkene. So we're going to react this alkene with, let's say, this hydrohalogen. Let's say we react it with HBr. So we can see that this HBr here, let me draw the electrons in a different color, right, is going to have 3 lone pairs here. And so what we see, we know that our bromine is electronegative, right? Our halogens tend to be electronegative, which means they have a high affinity for electrons. And so the electrons that make up this bond between the hydrogen and the bromine, for that reason, are going to be pulled closer to the bromine. They're going to be spending a greater period of time at the bromine as opposed to the hydrogen. And so that'll give this bromine here a partial negative charge. And because this hydrogen is being deprived of its electrons for some period of time due to bromine's high electronegativity, this hydrogen here is going to have a partial positive. And this partial positive hydrogen is thus going to be our electrophile. So now, looking at our alkene, we can see that the alkene here has these pi electrons. These pi electrons are negative, and so these negatively charged pi electrons make this alkene a good nucleophile. So our hydrogen here is our electrophile, and our nucleophile is our alkene here. So what do we see happening? Keeping that in mind here, actually. Oops. Let me redraw that. So what we can see happening then. Okay. What we'll see happening then is these negative, or the nucleophilic pi electrons here are going to go and attack the partial positive hydrogen here, right? This partially positive charge having hydrogen is going to be attacked. But we know that hydrogen can only have one bond. So if it can only have one bond, that means that the electrons that make up the bond between the hydrogen and the bromine, this must collapse. And so they collapse then onto the bromine. That breaks this bond. So that is going to lead us to end up having no longer an alkene, but an alkane. And that alkane is going to have this hydrogen bonded to it. And over here we will have a positive, so we have a carbocation. And we're also left, remember, the electrons in this bond have collapsed onto our bromine, so now we have a free-floating bromine in solution. And this bromine here is going to have 3 lone pairs. Let's put that other one in red here. So we're going to have 4 lone pairs. So having as opposed to the 3 lone pairs that we had before. So this 4th lone pair here is going to then impose a -1 formal charge on our bromine. And so because of that, we're going to have this negative, there are these lone pair here, go on and attack the carbocation. Attacking that carbocation, we end up with our final product for this reaction, where we have our hydrogen here and our bromine attached over here. So if you wanted to quickly draw out a more generic reaction mechanism for the hydrohalogenation of alkenes, I guess for your notes, you could look at something a bit like this, right? So we have our alkene, which we are reacting with, let's say, some generic hydrohalogen. So we're going to have these pi electrons attack our hydrogen, which then causes these electrons to collapse onto our halogen, giving us our carbocation. Remember that carbocation could be over here or over here. There is no preference in this case because we're dealing with a very symmetrical molecule, but we'll see that the idea of regioselectivity comes into play for other molecules or other compounds. But in this case, it doesn't really matter where our carbocation will be. It'll just be one of these two carbons. Again, we also can choose to include our hydrogen here. But again, when we're looking at line structures, we tend to omit hydrogen, so I'm not going to include it here. But we do have to include that free-floating bromine, as it's going to go back and attack our carbocation. So we'll have something like this, giving us the final product. Oh, excuse me. This is not a bromine. In this case, we're looking at a generic halogen. So it could be a bromine, but just for our reaction mechanism here, let us just replace that with some generic halogen. And so this is going to be our mechanism here. So if you were asked to show the reaction mechanism for a hydrohalogenation reaction, you have to be sure to include all of these steps and the intermediates. So, as I mentioned before, we haven't seen any regioselectivity here. Regioselectivity, as the name suggests, is referring to some sort of selectivity in terms of where our halogen would be attacking, or where our, rather more, I guess accurately, where our hydrogen would attack and thus form a carbocation, and then where that halogen would then attach later. So this idea of regioselectivity comes up when we're looking at molecules that are not as symmetrical as our last example. So let's take a look at such a molecule. So in the case of a compound like this, if we were reacting this with, again, let's say, HBr, what would this look like? Well, we can always start off with the double bond, or these pi electrons attacking our hydrogen, leading to these electrons collapsing on our halogen. But we could then have two possible intermediates here, right? We could either have our hydrogen attach to this carbon, giving us a carbocation over here, or we could see our hydrogen attacking this carbon, forming a carbocation over here. So now, which one is correct here? What is going to be the product that actually forms? Well, the answer to this question lies in the type of carbocation that we are dealing with, right? So we could either have our hydrogen attach here, or in this case, here, and so we have a different carbocation. In this case, we see that we have a tertiary carbocation, whereas in this case, we have a primary carbocation, right? We call it a primary carbocation because this carbocation, this carbon, is attached only to one other carbon directly. Whereas in this case, this carbon, our carbocation here, attaches to 3 different carbons. So this is tertiary and this is primary. So what we see here is that our tertiary carbocation is actually going to be more stable. And the reason is because it has more support. If you want to think of it in that way, this carbocation has more support. carrying a positive charge is something that's very difficult, right? It puts a lot of stress on that carbon atom here, and so having the support of other carbons in its vicinity, right, that it's directly attached to, helps it carry this burden. Whereas in this case, the primary carbocation only has one other carbon atom that is able to help it carry the burden of that positive charge, and so this is not as likely to form as this one is, as our compound here, or our intermediate with the tertiary carbocation, is going to be much more stable. So, keeping that in mind, let us continue with the mechanism. So we can see that our hydrogen here attacks the less substituted carbon here, the carbon that is bound to fewer carbons. And so we get our tertiary carbocation, and we still have our bromine here floating in solution. And so that bromine then goes and attacks the carbocation with its lone pair, leading to our final product looking a little something like this. Again, you can also include our hydrogen here, but it is not necessary, and I will be omitting hydrogens from the line structures, as that's just common practice. So this here is going to be our final product. So if you were asked for the final product, it would be this, and if you were told to draw out the mechanism, you would have to include all of these steps and your arrow pushing for sure. So hopefully this is making some sense. Alright, now that we've seen that, let's try to work through another example. But for this one, try to pause the video and give it your best shot. So let's say that we're starting off with our alkene looking something like this. So if this is our alkene, and we're reacting with our hydrohalogen, in this case HCl, please draw out the full mechanism and the final product, and let's see how this would play out. So I'm assuming that you've given it a shot, you've paused the video. So I'm seeing how this actually occurs. We can see that our double bond is going to start off by attacking our hydrogen, right? And this causes the electrons here to collapse onto our chlorine. This is nothing new. Hopefully you are getting familiar with this general arrow pushing mechanism. That is then going to lead us to forming an intermediate, right, with a carbocation. But there are two possibilities, as we saw before. We can either have our hydrogen attach to this carbon, forming a carbocation over here, or we could form this alternative intermediate where the hydrogen attaches to this carbon, forming a carbocation on this carbon. So which one here is going to be the major product or the major contributor here? Well, we can see that this carbon is a secondary carbocation, whereas here, this intermediate leads to the formation of a primary carbocation. And so this secondary carbocation is, I guess what it means, or what the name literally tells us, is that it is bound to two other carbons directly. And so this positive charge is able to be, I guess the carbon here, this carbocation, is able to share the burden of this positive charge with two other carbons. And so this is much more stable than this carbocation, which only has one other carbon to share that positive charge with. And so this is going to be less likely to form, as it is less stable. And so this is going to be the more likely intermediate that we will see, right? Just redrawing this, we will end up with a carbocation forming here, and our Cl, right, our chlorine, is then going to attack this carbocation with its lone pair, leading to the formation of our product here. Alright, so while we're on this subject, we might as well bring in some more fancy terminology, as it's what you're likely to encounter on an exam. So in the case of this problem, right, we came across two possible intermediates, which lead to two possible products. We can have the intermediate where we have our carbocation forming on, or we have an intermediate which has a secondary carbocation, or we can see one where we have a primary carbocation, which is going to look like this. So in each of these cases, they're going to lead to the formation of two different products, or into the formation of a different product. Here, we would end up with something like this, whereas here, we would end up with what is called a primary alkyl halide, right? Something, excuse me, these were CLs. I keep attaching bromines. Again, there's not necessarily a difference here, but the problem we were looking at was dealing with HCl, so we might as well stay consistent. So these are the two possible products that we would end up forming, and we call this one the Markovnikov product. Markovnikov product, and this one the anti-Markovnikov product. So the more likely one to form, the major product here, is going to be our Markovnikov product, and the minor product, the one that forms as a result or forms directly from the less stable intermediate, is going to be the anti-Markovnikov. So by definition, Markovnikov's rule tells us that the product that is more likely to form is the one that is formed directly from the more stable intermediate. So here we can see that of these two intermediates, this one is more stable, as it has a secondary carbocation as opposed to a primary carbocation. And so because this intermediate is more stable, the product that forms directly from this intermediate, which is this one, is going to be our Markovnikov product, and the one that forms directly from the less stable intermediate is going to be our anti-Markovnikov product. So our Markovnikov product here is going to be the major product, the one that is more likely to form. All right, so now that we have that terminology out of the way, let's look at another example just to kind of cement this in our heads. All right, let's very quickly look at this mechanism. Again, I won't be going into too much explanation here, as the video is already getting pretty long, but this isn't something that we haven't already seen, so let's give it a shot. So let's say we're reacting this with HBr. What would our reaction mechanism look like? Feel free to pause the video and give this a shot on your own, but I'll just be going right into it. So we can first have our pi electrons go towards our hydrogen, causing these electrons to collapse, giving us an intermediate, right? Remember, the more stable carbocation is going to be the one that is going to form. So here we could either form a primary carbocation or a tertiary one. So we will obviously form the more stable carbocation without our bromine floating in solution, which attacks the carbocation with its lone pair, leading to the formation of our final product, the Markovnikov product, which is going to look something like this. So if we were asked to draw our anti-Markovnikov product, that would be the one that forms as a result of this carbocation. So it would look something... I'm just putting it over here just for space reasons. This is a BR, something like that. So this would be our anti-Markovnikov product, and this is our major product, our Markovnikov product. So hopefully this is making some sense. If this video was useful, please show your support by liking and subscribing, and leave in the comments any questions you may have and suggestions for future videos, and I will see you in the next one.